Hello again. So, we take a shot at problem 11. You can probably see that I bought myself a new webcam, HD webcam. I don't know if it works very well with the program I'm using for recording, but we'll see. So, this is the information for the problem. I'll just leave it a little while so that you can read it. You can always stop and read it. So we go to the questions. We have actually two planes. Now the U and Z plane, complex planes, and we go from U to Z. So we work in the U plane, and then there's the Z plane. This is annoying, I can't see where I'm writing. We've had that problem before, haven't we? This won't do at all. Can I see? I can't see it at all. I need to be able to see what I'm doing here. So the Weierstrass P function goes this way, and we need to define a function going the other way, from the U plane to the Z, so to speak an inverse function. And that's what defined on this page. Now obviously we have the derivative here, dz du comes from this guy, and since u is at the bottom, it's minus. And we put in u for t. So the squared one. And we have z equal, when we take it at u1, now what is g of u1? I didn't get that. That's just a choice in the region, arbitrary choice. So we shall show that it is actually the inverse function. So it satisfies, du dz satisfies the correct differential equation. And then so that's A, we solve B. It's intolerable that I can't see the cursor. We know already from exercise 10 that it's a translate of the Weierstrass P function. Now let's just check. G goes from U to Z. So that means that the inverse, this is a multivalued function, of course. I'll just have to stop now until the cursor is visible. So back again, there were two problems. The one that the cursor was invisible, and the second that I didn't know what to do. We need to find a way to determine alpha, so it's actually in the lattice anywhere. So, and I didn't know how to do that, but I checked it, and it follows from this. If we let u tend to infinity, then this integral tends to 0, whatever the path may be. So if we have z equals g of u, then naught equals g of infinity. And that means the inverse function maps infinity the other way around, maps naught to infinity. And that's exactly what the Weierstrass function does. Every lattice point is mapped to infinity. So therefore we can conclude here that alpha lies in the lattice, so we may choose it to be, it's just the same as the Weierstrass of Z. Alpha lies in the lattice. Next, we have to show that different path doesn't change the value. And we'll show that explicitly. I believe that we have to go around the square root here. So let's make the path integral preparation, it should say. Can't read that myself. So we take the path integral around the unit circle. I don't really care about the branch, do we? I mixed notations there. So we need an integral of this function. This is 1 and this is minus 1, so it gives minus 2. That was very unexpected. Well, we'll just have to work on to paddle along and see. So that means around the square root, then if we take another path around the square root, a multiplum of 4 pi is added. So we'll just see what constant occurs when we do that with this function around one of the roots. So we better look at it in general. An example of what we are doing, I'm just doing this for my own sake, you may know it. If we take like z squared minus 2z and integrate it in a path around naught, the same one. So then the denominator, the denominator then we can write it as and then make a partial fraction decomposition. And if we multiply this by z and let z turn to 0, it's minus 2, so it's minus 1/2. And the same here, if we multiply by z minus 2 and let z go to 2, it's 1/2. So we'll just check. Half is z, minus half is z, plus 1. That agrees. And now, when we integrate around naught with radius 1, this integral will vanish, and by the residue theorem this gives minus 2pi times 1/2 so that is the integral it's minus pi. So how do we get this factor from the function? That was by a partial fraction decomposition. So I multiplied it by z and took the limit. So that's the derivative of this one at z equals naught, or rather 1 divided by that, minus 2. So I believe we should do the same with this guy. Take the derivative of it, and then insert the root That's just a guess. Can I prove it? Let's just write z. Z. And then we have a square root u, root of f u. The idea here was to write 1 divided by the square root of f, z, then take out 1 divided by the square root of z minus 1 root. Now let's assume the root is naught. That should make it much easier. But then maybe more difficult to generalize. I don't think so. So, and then I would write it 1 divided by something divided by square root z plus a holomorphic function. So I claim I hope we should be able to choose the constant c so that the path integral of this function will vanish. So it's just a question of determining c and then be lucky. So let's try to write it. That doesn't work at all. So I need to get an idea here. We could write it another way, say it's 1 divided by square root z d of z and then isolate f of x z. I've been teaching in high school too long. Now, if we insert naught in z, if that vanishes, then f will not have, I can't call it pole, a singularity at the center. So that's my claim. So what does that mean for our problem? Now let's assume it's true and then just perform the calculation. Well, I've filled the entire page with this, so we'll have to make a new page. Or maybe we can just do it on the right side here. Now, so the integral times the integral over the square root, which was minus that's not the right one. Where did I do that? 4i. And now g of naught, that's the great question. Now I have the problem of generalization. That should be a U, shouldn't it? Never mind. And then G3 must vanish for this to make sense. So, how to generalize this when the root is not 0? So we have a root E1, so it's some polynomial times z minus E1, and then we divide by this. And then let z tend to E1, which is, that's the derivative at E1. very, very confused. So we'll just take a break where I look at what I've been doing up until now, and actually I will stop for today and then carry on. I don't think I have time tomorrow, but then sometime during the weekend I will probably be able to work on it. So now it's 4 days since the last recording. 2 days after the last recording, I solved the problem, or I ended the last one. I was trying to make this claim that the square root as a doubly valued function equaled the path integral with various paths being possible. And it was all right when going from naught to u. That gave us square root u. Now we're in the real domain, so it's the real square root. Now if we went around u and then took a large circle with radius u and ended at u, then we had to subtract 2 square root u, giving us minus square root u. That was very good. And going another way around, I thought we'd have to subtract 2 square root u once again, giving us minus 3 square root u, which was not exactly what we wanted. The explanation turned out to be very simple. If we go 2 times around, I want black here, something, that's only 1 time around. If it goes 2 times around, then we get something times the exponential of 2 pi I, the half of 4 pi times I, minus, and that's exactly naught, because 2 pi I, the exponential of that is unity. So the point is that going around 1 time subtracts 2 square root u, the next time adds it. So that way we end up with a 2-valued function. This path integral can only give the 2 values it should. So now, having understood that, I wanted to work on a little more complicated function, and I chose this guy with 2 zeros, the denominator having 2 zeros, one at naught and one at z equals 2. And then I started looking a little at that. And then I tried, maybe Mabel knows this value. It did indeed, that equals pi. That was nice. Later on, I realized that it's possible that it knew the indefinite integral. Indeed it does, arc sine of z minus 1. So I've been quite stupid, because I've learned many years ago that to make life easy, use symmetric expressions. So I should of course have used like this guy. And then we would have got that. Or even better, just take arc sine and take the derivative of that, giving 1 minus z times 1 plus z. So that's the point. That's what I should have been doing. And that worked out quite nicely. So instead of that, instead, well, let's see if I can make another one. No, it's dead. So I'll just start up anew. Oh, we could have continued with that. That was nice of it. So let's do arc sine. So we define f of u equals and then I would like to establish that it equals arc sine of u as a multi-valued function. So I just want to take like u equals 0 equals unity. So we just consider this case. One could of course also take u equals 0 and see what happens there. We can just comment on that in the end. So we have the two zeros, and then we go from here to here. And we already know that that's pi half. Using the straight line. Now, another way is moving around like this. Bang. Or just bang. Now, here we go half a way around the singularity. So that means that it changes sign here, where we're going backwards. Here we go around this guy, so it changes sign again. This is where we go forwards. And it's pi, the value is minus pi and plus pi. That was the integral between these two singularities. So minus minus gives plus plus pi, that's 2 pi. So the next value we get by going once around is this one. So you see they all lovely agree. We would like naught to show that gives all multiply of pi, but I'm sure you can do that yourselves. We, of course, f of naught, just staying there, is naught. Now, if we go once around, like this, we add pi. The same if it goes once around here, I think. And going twice around, we add 2 pi, etc. So f of naught gives all multiply of pi. So that was very nice. So now I think I understand defining functions by path integrals. So it's now that I'm ready to start on problem 11, actually. I wasn't before, but now I feel ready to start problem 11. Okay, it's been a few days. I'm beginning to record the date, as you can see, because this turns out to be a marathon exercise for me. And now I've come to finding out that that it's well defined, that it doesn't depend on the path. That is, when we have a u and then go different ways to infinity, then of course it converges if it's a relatively straight line. But we want to show also that we may go different ways to infinity. These are the rules I've noted. So if we go, say, this way to infinity, or this way to infinity, then the integral should hopefully give the same. Now we can make a path first going along the red line up until some large radius r, and then turn around and then going back to u. That path integral vanishes. So if the path integral along this large circle will tend to 0 as r tends to infinity, then the two integrals, the two path integrals, give the same value, meaning that the result is well defined. So, and I believe we can do that by going around here. That's an integral, and it's to a large extent set three halves, and then dz, and we just go along a large circle with center in the center. So it's r d theta and it goes as r in minus half, meaning it tends to naught as r tends to infinity. So that means that as long as we evade all the three roots, then the path, and evades, that means that this area contains none of the roots, then it'll give the same result. So that means that the function we define here, g, is actually well defined. Now, we have to show that if we wind around E1, E2, and E3, we can only change the value by something in L. Now, if we go along a path, integrate along a path, and let u tend to E1, some of the roots, then we will, let's say this one is the, yeah, we'll just write that down. Then it will not necessarily give omega 1/2, but when we say that the inverse of this function is the Weierstrass P function, then of course we mean some restriction of it. A restriction to where there's no repeated values. So that means that instead of getting omega 1/2, we can get any value in the lattice corresponding to that point. And the same with E2 to infinity. So, if we, I can't show it on this graph, we'll just make a new one. This is the line from E1 to E2, straight line. If we make a path going around, like this, it will first, we'll have, I'll just put the direction on. There we go. We'll first get the integral from E1 to E2, and then going back on the other side, we'll be on the minus side, So we'll actually from getting from there to there and then back again going round and then taking the limit and oh that's never mind. Then it will actually give the integral from E1 to E2 twice. So going around so that's from E1 to E2, so that's this one minus that one. So this is in L. And now going around will give twice that, which means that we'll have an element of the lattice. And the same with the others. This one, omega 1 will cancel, and then we have half an omega 2. So going to E3 from E1 to around E1 and E3, or E1 and E2, that'll add respectively from E1 to E3 and from E2 to E3 and around there, that'll give omega 2 and omega 1 respectively. So it will, going around the roots, will always add some element in the lattice. So I believe this actually solves question B. Now we come to C. We must show this for a suitable branch. And we just have to check on the figure here. So we go from here to here. That gives us a path here in T space, and then that's called U. Actually, U is E2 when we compute this integral along this, the integral along this path. So we need to show that there exists a what was it called, a branch of the square root, so that they agree. Oh, there's only one that comes to mind here, and that's we already have the Weierstrass P function derived squared equals and that means that the Weierstrass P function itself, its derivative, is some square root. I claim we just have to take that branch and then we'll go back. Isn't that obvious? I feel it is. The question of making it formal I would like to make it formal because we are going to do it again down here in the next exercise. I just saw it when I started. So I'll just make this make this argument formal that we have to use the same range. That requires a little work, and I won't do it while recording, but I'll just show the result when it's ready. So what was the problem really? So we've got the path. Where t goes from 1 to 0, and we've got the integral. Along this path. So it's just plugging in. The derivative here is the square root of it all times the derivative of the internal function and we have chosen the same branch for the two square roots, so they cancel. Now, what was that? Oh, that was exactly what we had to show, wasn't it? Yes, it was. How lovely. So, I don't know why I couldn't do that immediately. So, let's try to solve the rest of the problem. Last time I managed to solve part C. So, we have a path from infinity to E2 along the curve defined up here. Then we wind once around E2 and go back to infinity along the same path. Oh, but we have already done that with the square root. So going from E2 to infinity gives, or what was it? There's a problem with the sign here, really. E2 to infinity. I did get this. Well, and then when we go once around and then out, it's the opposite sign. So it should be minus omega 2. Well, I get minus omega 2. Now, describe how it can be made to give all pre-images of U. Yeah, that's the grand total. So we have given a U, and then we solve the equation. And I didn't need this. Omega 1, omega 2, so this is the fundamental domain. And I want first a pre-image in this domain, and I want it so that the curve has no self-interactions. Self-intersections, sorry. So here's omega 2 halves, omega 1 half. So, and with this one we need as well. Now, it moves down towards this, the value E1, and then it turns back to infinity. So here the same value, we have two solutions. If one is here, then the other is here. So I want to have one that where we go down to 0, and the curve will have no intersection, self-intersection. So if we have a value here, P is an even function, so that minus the value down here, and then we add omega 2 to get up here. Oh, that was not my point. I wanted to have one in here. Well, here then plus omega 2 plus omega 1, so they give the same. The point is, I want to find a domain. I believe that it should be in here, so that when we take a path going down here, then we get this pre-image. And then the other ones, minus the one plus the minus the 1 plus this lies up here. Well. I don't like to go out here, because I have a feeling that they are twice anyway. Then we will have the value of some point twice. I would like the path not to have a self-intersection, in case we should go around E1. That bothers me a little. Maybe I shouldn't worry about it, really. So I'd like this guy to come from something in this parallelogram. But it seems that it doesn't. course, if it came from there, then it should be, this should be down there, this should be down there, and this should be down there. So it should be 4 to 1 in general. It's only a 1, or the Weierstrass P function is 2 to 1 in general. So we have to not take it so seriously. Oh, I think we should maybe go down like this. Let's try that instead. Go down here. I still don't like it really. So if we take a point like here, we can take minus the point and add omega, add minus the point and add this to end up here. If we take a point here, we can take minus the point. I don't think we can come in here. Okay, so let's use this. This is our fundamental domain. So we choose a pre-image in here. And then we use the curve of now, where did that go really? I think that went here. So this is our Z. And then we have this guy, this curve. So the path equals gz, where g goes from 1 down to 0. Then we take the Weierstrass P function, of course. And we just copy the integral along the curve. And we just have to check this curve. It goes from when t is 1, it's our image u, and when t is 0, it's infinity. Better write g here. Now that's never mind. So that's the integral from 1 to 0. And then the derivative of gamma, the derivative of p, Weierstrass P function, times z dt, and as in the other, we would use the same branch of the square root. So these cancel, leaving us with minus z. That was a little surprise. So this integral gives, with the path I chose, minus the one I wanted. That agrees with C, of course. So to get plus z, so going from here to here gives minus omega half. So how do we get the plus, the positive one? So the one solution I say is, instead of doing this one, we take minus z and then go in that way. Then the integral should give z. So that's the way to obtain the principal solution. And using this one gives z minus z, oopsie. Going this way gives minus z, and then we need to go up. That could of course be accomplished by going once around E1 as well. That would change the sign, but we learned that when doing the square root. And then to add omega 1 and omega 2, what we need to do is to go around two solutions, or two stationary points. Actually, I used that in my answer to B, that I wasn't able to find the values giving omega 1 half and omega 2 halves, but the same method. So I probably should have solved this in another way, because the method I used here in B now gives all the pre-images. So that was really a big problem for me, this one. So I had to wrap my mind about defining a multi-valued function by a path integral. And I had many problems doing that. Well, in the end, I think I got through and I have learned a lot. So there you are.